Now, note that if y and z are independent, then the conditional distribution function of conditional PDF or PMF of y given z would be same as conditional PDF of y. So, that means you will be integrating psi y with just PDF of y, and which gives you expected value of psi y. So, if y and z are independent, then expected value of psi y given z would be same as expected value of psi y for any function psi. Similarly, variance of psi y given z, again here, because the conditional PDF of y given z will not depend on z, it would be same as the PDF of y. So, that means you will be finding out the variance of psi y with respect to the PDF of y or PMF of y, and that is nothing but variance of psi y. So, which makes sense also, because if y and z are independent, y should expected value of psi y given z should depend on z, or variance of psi y given z should depend on z. Now, let us do this example. So, let x1, x2, x3 be a trivariate random vector, which PDF is given by 1 upon x1, x2, if 0 less than x3 less than x2 less than x1 less than 1, and 0 otherwise. This PDF we have seen earlier in one of the earlier modules. We found out the marginals of x1, x2, x3, and we did so many things. We found out conditional PDF of various variables and so on. Now, let y1 is 2 x1 minus x2 plus 3 x3, and y2 is x1 minus 2 x2 plus x3, and y is same as x1 plus x2 x3. Find correlation between y1 and y2. For a fixed x2 belonging to 0 1, find x2 y given x2 is equal to x2, variance of y given x2 is equal to x2, and covariance between x1 and x3 given x2 is equal to x2. Note that if you see the last module, we had considered it, and we had seen for a fixed x2, this range can be broken into two parts. If x2 is fixed, then 0 x3 less than x2 and x2 less than x1 less than 1. So, that means if this x2 is fixed as a function of x1 and x3, this range can be broken out. Here also variables x1 and x3 can be broken out. So, it looks like given x2 is equal to x2, x1 and x3 would be independent. So, this covariance, one can directly say that this would be 0, because given x2 is equal to x2, x1 and x3 are independent. So, let us try to do these one by one. So, first I have to find correlation between y1 and y2. For that, let us find covariance between y1 and y2, which is covariance of 2 x1 minus x2 plus 3 x3, x1 minus 2 x2 plus x3. I know that covariance is linear, so I can take the term by term covariance. So, this is same as 2 times covariance between x1 and x1, which is same as 2 times variance of x1. 2 and 2 makes it 4, 2 and minus 2 makes it minus 4. So, minus 4 times covariance between x1 and x2. But covariance of x2 and x1 and x2 also comes through covariance of x2 and x1. So, minus covariance x2 x1. So, minus 4 covariance x1 x2 minus covariance x1 x2, that becomes minus 5 x1 x2. Then 2 times covariance x1 x3 plus 3 times covariance x3 x1. So, that gives me 5 times covariance x1 x3. Then minus covariance between minus x2 and covariance between minus 2 x2, that gives me 2 times variance of x2. So, 2 times covariance of x2 and x2, which is same as 2 times variance of x2. Then minus covariance of x2 and x3, then minus 6 times covariance of x2 and x3. So, that gives me minus 7 times covariance of x2 and x3. Then covariance of 3 x3 and x3 gives me 3 times variance of x3. So, that turns out to be this quantity. If I have to look at variance of y1, which is variance of this quantity, which is same as 2 square variance of x1 plus variance of x2 plus 3 square, which is 9 times variance of x3, minus 2 times covariance between x1 and x2, covariance and 2 x1 and x2. So, that becomes minus 4 times covariance of x1 and x2. Then 2 times covariance 2 x1 and 3 x3, that means 2 into 6 times covariance x1 and x3, that is 12 times covariance x1 and x3, and then minus 6 times covariance between x2 and x3. Similarly, one can get variance of y2 as this, and correlation between y1 and y2 would be nothing but covariance divided by square root of the variances of two variables, which is variance of y1, variance of y2. So, I need to find variance covariances, variances, and so on. So, I know that for any function psi from R3 to R, if I have to find exponent psi of x1, x2, x3, you integrate psi of x1, x2, x3 along with PDF in the whole range R3. But my PDF is positive only in this range x3 less than x2 less than x1 less than 1, and that PDF is 1 upon x1, x2 in this range. So, 1 upon x1, x2 integrated with psi x1, x2, x3 in this range. So, here I fixed first x1 as a free variable, x1 as a free variable can go from 0 to 1. Then for a fixed x1 I see where x2 goes, for a fixed x1, x2 goes from 0 to 1, so this is x2. Now, x1 and x2 are fixed. So, for fixed x1 and x2, x3 goes from 0 to x2. So, this is what exponent psi of x1, x2, x3 would be. Now, if that is the case, then exponent of x1, just replace here psi of x1, x2, x3 by x1. So, it becomes 1 upon x2, and you get this as half. You can get similarly exponent of x1 square. So, you put it here x1 square. So, that gives me x1 by x2, and integrate over the same range, you get 1 by 3. So, using this, you can get similarly expected value of x2 as this quantity, expected of x2 square as this quantity, expected of x3 as this quantity, expected of x3 square as 1 by 27. So, these are simple calculations. Expected of x1, x2 is this quantity, because we have derived the expression for expected value of psi 1 x1, x2, x3 for general psi. So, you have to just change psi with x1, x2 or x3 square or x3 and so on, and you can get all these values. Similarly, expected of x1, x3, you replace psi by x1, x3, you get 1 by 12. You replace psi by x2, x3, you get expected of x2, x3, which is 1 by 18. Variance of x1, one can get expected of x1 minus expected of x1 whole square, which is 1 by 12. Variance of x2, similarly, one can get expected of x2 square minus expected of x2 whole square, which is 7 by 144. Variance of x3, expected of x3 square minus expected of x3 whole square, this turns out to be 37 upon 1728. Covariance x1, x2 is nothing but expected of x1, x2 minus expected of x1 into expected of x2. This we have already found. This is found, and if you put those values, I get 1 by 24. Similarly, I can find covariance of x1, x3, which is expected of x1, x3 minus expected of x1 into expected of x3, and all these we have found. So, if you put those values, I get 1 by 48. Covariance of x2, x3 is nothing but expected of x2, x3 minus expected of x2 into expected of x3, which is 7 by 228. So, therefore, covariance of y1, y2, I go back and see what is the expression for covariance of y1, y2, which involves covariance of x1, xi's. So, this is over here, it will involve covariance of xi's. Similarly, variance of y1 will involve covariance of xi's, variance of y2 would involve covariance of xi's. So, if you put all those values through simple algebra, you get variance of y2 as this quantity. Before that, you get covariance between y1 and y2 is 31 upon 576. Variance of y1, which is same as this, that you get as 295 upon 576. So, similarly, variance of y2, you put various values of covariances and you get 133 upon 1728. So, correlation between y1 and y2 would be nothing but covariance between y1 and y2 divided by the square root of variances, and this, if you calculate, turns out to be 0.2710. So, I cannot conclude from here that y1 and y2 are linearly related. If it was, this value was very close to 1, I could have said there is a strong evidence that y1 and y2 are linearly related. Now, given x2 is equal to x2, we have seen that x1 and x3 are independent random variables. This we saw in the last module as well, because the same example was considered in the last module, and their conditional PDFs are given by this. These marginals we have already found in the last module. This turns out to be this quantity for x2 between 0 to 1. This you get from the fact that conditional PDF is proportional to the joint PDF, and joint PDF is nothing but some factor of x2 divided by x1. So, x2 by x1. So, if you this you can get from the joint PDF of x1 and x2, this you can get from joint PDF of x2 and x3. So, it will be proportional to joint PDF of x2 and x3. So, this. So, f x 2 x 2 turns out to be this. This anyway we have found in earlier modules. Let us look at what is expected loop y 1 given x 2 is equal to x 2, which is same as expected loop x 1 x 2 x 3 given x 2 is equal to x 2. Now, x 2 has been fixed at small x 2. So, this is same as small x 2 and that is fixed. So, that goes outside. So, this becomes expected loop x 1 x 3 given x 2 is equal to x 2. But given x 2 is equal to x 2, I know that x 1 and x 3 are independent. So, if they are independent, then expected value of product would be same as product of expected values. So, this is same as expected loop x 1 given x 2 is equal to x 2 multiplied by expected loop x 3 given x 2 is equal to x 2. So, it would be the product of expectation with respect to the same conditional distribution. And the conditional distribution involved here is x 2 is equal to x 2. So, this is what it turns out to be. Now, one can find expected loop x 1 given x 2 is equal to x 2 because you have found the PDF of x 1 given x 2, which is this quantity. So, this turns out to be this quantity. Similarly, expected loop x 3 given x 2 is equal to x 2, you have found out the conditional PDF of x 3 given x 2. So, this turns out to be this quantity, which is nothing but x 2 by 2. So, expected loop y given x 2 is equal to x 2, which was times x 2 times expected loop of x 1 x 3 given x 2 is equal to x 2, which is same as x 2 times expected loop x 1 given x 2 is equal to x 2 into expected loop x 3 given x 2 is equal to x 2. These two quantities you have already found, x 2 is already there. So, you get finally this quantity. Now, you can talk about expected loop y square by the same logic. This turns out to be expected loop x 1 square, x 2 square, x 3 square given x 2 is equal to x 2. But here x 2 is being fixed at small x 2. So, that goes outside. So, x 2 square, then expected loop of x 1 square. So, this will be same as x 2 square, expected loop of x 1 square, x 3 square given x 2 is equal to x 2. But again x 1 and x 3 are independent given x 2 is equal to x 2. So, this will be same as expected loop x 1 square given x 2 is equal to x 2 multiplied by expected loop x 3 square given x 2 is equal to x 2. Now, these conditional PMFs you know, PDFs you know. So, you can find out these quantities. So, expected loop x 1 square given x 2 is equal to x 2 is nothing but multiply x 1 square with joint PDF of x 1 given x 2, you get this quantity. Solve this integral, you get this quantity. Similarly, expected loop x 3 given x 2 is equal to x 2, you have to integrate x 3 square with conditional PDF of x 3 given x 2, which is same as this. Integrate this, you get x 2 square by 3. So, variance of x 1 given x 2 is equal to x 2 is same as expected loop x 1 square given x 2 is equal to x 2 minus expected loop x 1 given x 2 is equal to x 2. Since given x 2 is equal to x 2, x 1 and x 3 are independent. This is what we saw before. We can say that covariance between x 1 and x 3 given x 2 is equal to x 2 is 0, because if you know that if x and y are independent, their covariance is 0. Now, let me give this as a take home problem, which is very similar to the last problem which we did. The only thing here is we are dealing with a discrete random vector. So, let x 1 x 2 x 3 be a discrete random vector with joint PMF given by S. Let us define the y 1 and y 2 in the similar fashion and y in the similar fashion. Find correlation between y 1 and y 2. For fixed x 2 belonging to 1 to 3, find expected loop of y given x 2 is equal to x 2 and variance of y given x 2 is equal to x 2. So, this will give you some exercise about finding conditional expectation and variance. Now, before I conclude this module, let me give a summary of the things I will be doing in the next module. In the next module, we will introduce the joint MGF of a random vector and we will study its properties. We have seen how MGF of a single variable is useful in finding the movements and other properties, even studying the equality of distribution. Now, similar thing we will do now for the random vectors. So, this was all for this module. Thank you for your patience and have a great day.